Okay, welcome back to part 2 of the lecture. Right, in this part, we'll try to explain why Einstein's idea is actually better at explaining the photoelectric effect than the classical wave theory. Right, so this is the idea that Einstein put forward. Right, that instead of treating electromagnetic radiation as a continuous wave, Einstein suggested that the electromagnetic radiation are actually discrete packets of energy that behave like particles. Right, so Einstein is suggesting that light actually behave like packets of energy as if they were particles of energy. All right. And a photon, this is a formal definition that you should know, all right, is a quantum of electromagnetic radiation. That means a photon is a packet of light energy. All right. And each photon is energy is actually defined by this equation E equals to HF. Right, so the energy of a photon is directly proportional to the frequency of the electromagnetic radiation. That means H is a constant. Alright, so if the frequency is higher, the photon has higher energy. Can? Alright, so we'll do one simple example here to try and understand what's going on. Where H is a constant called Planck's constant, alright, which Planck has a very long story also, quite interesting in quantum physics, alright. Maybe you can ask your tutor to tell the story in the classroom, right? But Planck's constant is given as 6.63 times 10 to the power minus 34 joules per second, which is a very small number. Okay, so if we want to determine the energy in a joule, in joules of a high energy gamma photon or frequency 10 to the power 26 hertz, all right, we'll just take the frequency of this gamma photon and multiply by Planck's constant here, right? So 6.63 times 10 to the power minus 34 times 10 to the power 26, that gives me 6.63 times 10 to the power minus 8 joules, which is a very small amount of energy. All right. So and gamma photons is considered high energy photon. All right. So even a high energy photon is a very small amount of energy. All right. So because of the fact that there's a lot of negative powers, all right, instead of using joules as the unit for energy in quantum, we have a tendency to use another type of unit called electron volt. All right. So electron volt is normally used in this chapter, all right, because it nicely represents very small numbers well. Okay, so what is the definition of 1 electron volt? Right, it's the energy gained by electron when it's accelerated across a potential difference of 1 volt. All right, so I'll try to give you an example here of what it means. All right, so if I have a battery here that is 3 volt, okay, if the electron is accelerated across somehow in this potential, right? So let's talk about free electron. Right, so if the electron is accelerated towards this direction, right, because electron should be attracted to the positive plate, right, the potential difference across the plates is 3 volt. So if you learn in electric fields, you should realize that if the electron move from here, which is the negative aspect of the plate, to the positive aspect of the plate, right, it basically gains 3 volts. So the energy gained by the electron is equal to Q times delta V. Right, so this will be equal to this delta E lah. So it's the charge of the electron, which is 1.6 times 10 to the power of minus 19, multiplied by delta V, which is 3. Alright, so it's basically this number times this number in joules. Alright, but instead of writing this, we can write 3 EV. Alright, okay, otherwise I have to punch the numbers out lah. So 1.6 times 10 to the power of minus 19 multiplied by 3 joules. That's also correct lah. But I can also represent it by 3 EV. What's the use of this? If I'm talking about electron which gain energy of 3 EV, I know this electron is accelerated over a potential difference of 3 volts. Can you see that it gives me two sets of information at the same time? Right, so that's why this EV is a useful way of representing energy at this level. All right, so you can memorize this if you want, but normally I'll just try to figure out logically lah. To convert from EV to joules, multiply by 1.6 times 10 to the power of minus 19, right? So this 3 EV, how to convert to joules? 3 times 1.6 times 10 to the power of minus 19, right? This is joules. You realize that this is this value over here. It's the same. Right, obviously to convert from joules to EV, you divide by 1.6 times 10 to the power minus 19. right? So I'll give you a few moments to try question 2, right? You can pause the video and try, all right? Please do, because otherwise it will affect your learning, all right? I will carry on so that the video isn't too extended. All right, pause the video for however long it takes to try question 2, all right? I hope you have already tried question 2. This is the part where I will go through question 2. All right, so if we look at the question, I want the maximum energy of a photon of visible light. If we look at violet and visible light, right, which one has higher frequency? Because the one that has higher frequency has higher energy, because the relationship E equal HF, right? So the one that has higher frequency must be lower wavelength, right? So violet light is the one I'm interested in, right? So E max equal to HF max. F max must associate itself with the lowest lambda, right? Actually, we discussed this in an earlier lecture, right? So I'll just change F to C divided by lambda, right? Why? Because V equal F lambda, right? It's an equation that governs all waves, right? So you get Planck's constant multiplied by speed of light divided by wavelength of violet light, right? And you get, in terms of joules, right? Because I want EV, right? So you divided by 1.6 times 10 to the power of minus 19, okay? So you get 3.11 EV, right? This is the maximum energy of a photon of visible light, which corresponds to violet. Okay, again, please pause the video to do question 3. Right, if you are confused, this is the talking about the source. Right, remember we talked about PHET app. There's a source of light. I could vary the intensity. Right, the intensity is actually to vary the power. Right, so it's the power associated with the violet source. Right, so you try yourself. Right, then I'll come back and go through the question. Okay, this is the part where I'll go through the question 3. Okay, determine the number of photons emitted by a 60 watt violet light source. Wavelength of violet light is 400 nanometers. Right? So if the power is 60 watts, all right, power is total energy of light source per second, right? So this can be thought of as number of photons per second multiplied by energy of each photon. In this case, it's violet, right? So actually, I can steal this value 4.97 times 10 to the power minus 19 from here because I already calculated. But of course, you can recalculate if you want, all right? And this is the energy for one packet of light. Alright, so or one photon. Alright, so how many photons per unit time will give you 60 watts? So it's N over T times the energy of one photon equals 60. That's how you find N over T. Alright, so N over T is 1.21 times 10 to the power 20 photons per second. Right, so at a 60 watt violet light source will emit 1.21 times 10 to the power 20 photons per second. Right, what this question is trying to explain to you is that when you increase the power of a light source, what you're increasing is not the amount of energy per packet of light, but you're just increasing the number of packet of light per unit time. Understand or not? So if this 60 become 120, then this N over T will become 2.42 times 10 to the power 20 photons per second. But each photon still carry the same energy as defined by HF. Alright? Alright, so let's go to photoelectric effect. What actually happens in the experiment that gave Einstein his Nobel Prize? Right, this is what Einstein suggested. All right, the electrons that are emitted from a cold metal, all right, this is the formal definition for photoelectric effect. Right, it refers to the emission of electrons, also known as photoelectrons, but they're just electrons, emitted from a cold metal surface when electromagnetic radiation of sufficiently high frequency falls upon it. All right, in 1905, Albert Einstein explained this phenomenon based on the idea of photons, which we were just introduced to earlier. All right, so let's try and understand what's going on here. Right, so we have a light source somewhere here, right, shines the light, right, in terms of, now Albert Einstein said light is not a wave, it's a photon or a packet of light. Okay, so a packet of energy, right? So as it comes down towards the metal surface and enters the metal surface, somehow the electron emits, assuming that it's of sufficiently high frequency, right? So what happens is that the photon has energy HF. As the photon enters the metal surface, the metal surface electrons will absorb the photon. If the energy of the photon is sufficient for the electron to escape the metal surface, the electron will escape the metal surface. Then, after the electron use up the energy to escape the metal surface, whatever is left over is Ke. Alright, so we go through one more time. Alright, the photon is a packet of energy. When it enters metal surface, it hits an electron. The electron takes in the energy. Then it thinks about it. Do I have enough energy to escape the metal surface? That means overcome the forces holding the electrons in the metal. Right? If the answer is yes, then I can escape the metal surface. Right? If I just nice have the same amount of energy from the photon I absorb, right, have the same amount of energy as the amount of energy I need to overcome the forces holding the electron in the metal, then I come out with 0 Ke. But if the photon give me more energy than I need to overcome forces holding the electron in the metal, then the excess is my Ke as I come out. Okay, can? So hopefully you understand that, right? The photoelectric equation is given formally here as electron provided by a single photon, which is HF, right, is equal to work function of metal, right? So work function of metal is basically the energy used to overcome the forces holding the electron in the metal. And obviously this is different for different metals, right? That's why in the previous lesson I talked about sodium and zinc. You can see that the maximum lambda is different, which means the minimum frequency is different as well. Okay, then of course whatever is left over after you overcome the forces is Ke. Okay, so work function energy, right, phi, right, it's called phi, equal hf naught, all right, of a metal is the minimum energy of a photon to cause emission of an electron from the surface of the metal. Work function energy depends on the nature of the material of the metal and its surface condition. All right, that's why if you look at the formal definition, it says cold metal. And obviously the type of metal matters. All right, so that means sodium and zinc will have different work functions. All right, technically, I'm going to tell you that work function energy is not formally mentioned in your syllabus. But if you look at the last 20 years of quantum physics, right, it's used almost everywhere. All right, so that's why we choose to just mention the term. And in any case, our work function energy is closely associated with threshold frequency, right? And threshold frequency is a term you are required to know, right? So that's why we decided to teach you work function energy anyway, lah. All right. So whatever this work function energy is, if you equate it to hf naught, all right, then you can find f naught, which is the lowest frequency of electromagnetic radiation that gives rise to the injection of electrons from the metal surface. All right. So threshold frequency depends on the nature of the material, the metal, and its surface condition as well. Obviously, because threshold frequency is just derived from work function energy, right? So I'll try and explain this quickly, right? Remember that what we discussed is that if the photon, HF energy, right, is just nice equal to the work function, then the electron will emit with Ke equal 0. Right? So that means for photon, for an electron to be emitted from the metal, the HF of the photon must be greater than the phi of the greater or equal to than the phi of the work function. And if I look at HF greater than or equal to phi, that means HF is greater than or equal to HF naught. Right? So what is this? Can you see that this is the minimum energy the photon need for the electron to be emitted with just nice 0 Ke? Can hopefully you understand that, right? So I'll give you a number I'll give some numbers maybe a diagram to try and understand this better, right? So imagine you have a well, right? Then this well, the bottom is not the same height, something like that, right? So there's an electron here, there's an electron here, there's an electron here. Okay, I'm not going to bother about height of the well, but you can think of it as to escape the well, this electron require 3 joules, right? If the electron is deeper inside the metal, right? So you can think of this as hypothetically the metal surface. If the electron is deeper inside the well, do you think you need more energy or less energy than 3 joules to escape? Right? Should be more. So this could be 4 joules. This could be 5 joules. Right? So let's say a photon comes in, right? So hypothetically a photon comes in. Sometimes you draw a photon like that. Right? My drawing not very good, but this is supposed to look like a wave. Yeah, okay, it looks horrible. Let me try and redraw it one more time. Okay, I'm never going to draw it very well. Okay. Okay, so a photon looks like a wave. Let's say this photon is a packet of energy with uh, 5 joules. 5 joules? 4 joules lah. Okay, let's say it's 4 joules. Right, so if this photon has energy 4 joules and it hits this guy over here, right, this guy is going to use 3 joules of the 4 joules he absorbed from the photon, and then he's going to come out with Ke equal 1 joule, right, according to this equation over here. Because this was 4 joules, the amount of energy he need to escape is actually 3 joules, and the leftover energy is his Ke, 1 joule. Alright, then if we go by conservation of energy again, this 4 joules photon, because it's of the same frequency or wavelength, right? So it's one packet of energy with all the photons having 4 joules. If he hit this one, right, he used all 4 joules to escape. So this electron escape with Ke equals 0 joules. Basically, it escaped with no Ke. Alright, so you just count the metal and probably stay stationary there. Theoretically possible. And this 5 joule electron, if he absorbs a photon, cannot escape at all. Can understand? Alright, so this is what happens when there's some photon being shone on electrons in the metal, right? The easiest to remove electron, this one, is defined as, this energy is defined as the work function energy of a metal, right? Because this is the lowest amount of energy required to cause the electron to come out of metal. So it's the easiest to remove electron, right? But if I change the light to, let's say, let me try a different color. Say instead of 4 joules, I change to another light that is 3 joules. Can you see that now only this guy will come out, and this guy will come out with energy equals 0, right? Ke equals 0. Okay, sorry. Okay, let me try and do this nicely, right? This Ke of this electron will be equal to 0 joules. Alright, and therefore the photon energy here is actually equal to the work function energy, because this is the work function, right? The minimum energy for the electron to come out of a metal. Alright, and therefore I have this equation over here, and therefore I get this one. Okay, can? Alright, so anyway, that's threshold frequency. It's the lowest frequency because if you have higher frequency, which is this red color one, this will be your work function. So if your work function here 3 joules divided by h, you'll get threshold frequency, right? So if you get higher than threshold frequency, no problem. Sure, the electron can come out and it come out with Ke, right? And threshold frequency is associated with threshold wavelength, right? So we talked about why if this one is lowest, this one is highest before, so I won't go through it. But they are again related by the formula V equal F lambda, right? So if this one is max, this one must be, sorry, this one is minimum, lambda must be maximum, right? So that's why in the applet, we looked at the maximum lambda instead. But I can always find F minimum from lambda maximum because I can always use this equation where V is actually speed of light. Okay, moving on. Right, okay, I think the lesson has been quite long. Right, I'll just try and end on with 2 examples and I'll carry on in the third part. Right, so from the definitions above, we have this. Right, so we've covered this already. So I'm not going to talk about this again. Okay, please pause for a moment to try and do question 4. Okay, we come back to address question 4. I hope you have tried it. Right, what's the work function of the metal in joules? Right, so if you look at just the Einstein's equation, energy of photon is work function plus maximum kinetic energy of the electron. Alright, so the frequency of incident radiation is the photon that they shine on the metal. Right, so this is HF energy. Right, the work function of the metal is to be found, and the Ke of the electrons emitted is actually 1 eV. But if I want to convert to joules, I just multiply by 1.6 times 10 to the power minus 19. So that gives me work function of metal to be this. Right, threshold wavelength, right, you can use this formula over here if you want to, but generally I don't memorize this formula. I think it's quite self-derivable. Right, so once you get that, pressing calculator, you should get lambda is 5.9 times 10 to the power minus 7 meters. Alright, so wait, am I missing something? Calculate the energy. Yeah, actually I think that's all. Right. No, I'm not missing anything. Yeah, it's correct. Okay, last part. Alright, question 5, I'll talk about this I think in the next lesson. Alright, but you can think about this before you approach the next lecture. Alright, so see you in the next lecture.